All right, so well, we're continuing on, well, obviously, with physics in our first unit, all about motion. And on Thursday, we looked at distance and displacement. And today we're going to take it a step further, and we're going to look at something called speed and velocity, which are actually two different things. Because speed, which is a nice V, is the total distance traveled divided by the time taken to travel that distance. So our formula here is V equals delta D, which is our distance, divided by T or delta T. Doesn't matter. It's the same thing, the change in time or how much time's gone by. All right, and again, this is where delta D, well, I'm going to throw that in there after, is the distance. Now, here's the key, is that on Thursday, we looked at distance as being a scalar, which means it does not have direction. Now, that also means speed is a scalar. All right, so when we're looking at speed, we're just talking about magnitude, just the size. All right, now velocity is also denoted, or the variable is a V, but it's got an arrow over it, and that's because, well, it is a vector. All right, whoops, trying to write that in there. So the formula, well, how velocity is found is it's the total displacement or change in position divided by the total time for that displacement. And so our formula for velocity is going to look exactly like speed, except for one distinction. We have that arrow over top, which means we're dealing with vectors. So this delta D here is a displacement, not distance. And again, we have a delta T or a T down in the bottom. There we go. So there's our two formulas. One involves distance, one involves displacement, which can sometimes have the same magnitude and sometimes not. So speed and velocity are not always just the same number, with a direction being the difference. So we'll get into that as we go along here. Now, the other thing is that uniform motion. It's a term that's referred to an object is said to have uniform motion if its velocity remains unchanged. And when you have that going on, because there's two aspects of velocity, that means there's two things that can't change. So in other words, there is no change in magnitude or the size or direction. So there's two things that don't change if you have uniform motion. All right, so you keep going the same direction and the same magnitude. All right, so well, we're going to look at these two definitions, finding speed and velocity. All right, so I have example one here. An airplane is located 180 kilometers east of the airport. Takes 3 hours to land in a cornfield, which is 320 kilometers west of the same airport. What is the average velocity for the plane? Velocity. So again, here's what I'm going to be using in terms of velocity. I got my V is equal to delta D, again with a little arrow, over T, or delta T, again, doesn't matter. Now, what variables? I like to look at what we got here. Now, this is something that was a little bit confusing, and it is confusing when you're talking about displacements, is I have an airplane is located 180 kilometers east of the airport. Now, what that is telling me, it didn't tell me that the airplane moved. So that's not a displacement here. This is, in fact, a position vector, because it's not telling me it moved. It's telling me where it is in reference to some point. So I have a D1, a position vector of 180 kilometers east of my reference point, which happens to be the airport. It lands in a cornfield, which is another position vector, where it's telling me it's 320 kilometers west of the same airport. So that is its final position. All right, so this is going to be D2, where we have now 320 kilometers west of the airport. All All right, so those are two position vectors. That is not my displacement. We will get to that. The airport takes 3 hours. It takes 3 hours to land. So that is going to be our delta T, or our T, same thing. So T equals 3 hours. All right, now we need the displacement to find my velocity. I have two position vectors, and this comes down to what we looked at in displacement on Thursday, where my delta D is equal to D2, put an arrow over it because it's got direction, minus D1. All right, so now I can find out my delta D. Now here's the trick with vectors, and this is something we are going to deal with a lot, is that they have a different direction. All right, and so when I plug into my formula here, I have to take that into account. All right, now, because again, when I do a compass rose, north, east, south, west, north is always on the top, east is always on to the right. So I always tend to, well, not tend to, but most of the time, I will make them positive, where I will make west and south negative, just like a graph. All right, and so because east is positive and west is negative, so now I'm going to find my displacement. Watch what happens here. D2 is 320 kilometers west, but I have said that west is negative, so I'm going to put in a minus 320. Then I subtract D1, which is 180 kilometers east. Well, I said east is positive, so that's going to stay at 180. All right, now, when I'm finding my displacement here, I subtract those two numbers. Minus 320 minus 180, that is a minus 500. But that's not my displacement. I'm now going to convert it because I have this vector symbol here. I have to now write it down as a vector, and it has a size of 500 kilometers. All right, but the direction, the sign is negative, which means this means our displacement has a direction of west because the sign is negative, and I already said east is positive, west is negative. Now I can go over and figure out my velocity because I have my displacement. I have my 500 kilometers west. There's my displacement. All right, the time, that doesn't have any direction on it. That is my 3 hours. I now divide those two numbers, and let's see here. What am I getting? I got to get my calculator out. 500 divided by 3. Oh, decimals. So we always go to 2 decimal places. All right, so 1.67. I think it was, it said 0.666666. So I rounded 2 decimal places, 0.67. The units are kilometers per hour, as I can see with my bracket here, kilometers per hour. And it is a velocity, which means it has direction, and the direction has to be west. So there's my velocity. A little bit of work going on there to find that. All right. Any questions so far? I'll check the chat. Oh, we seem like we're okay. All right. All right. So now I'm moving on to example 2. Same idea here. All right, a car drives 215 kilometers west to Waterloo. That's where I went to university, or in the city anyways. And then drives 115 kilometers east to Toronto. And then finally, 80 kilometers west to Guelph. If the entire trip takes 6.5 hours, which it probably does, find the average speed of the car. All right, and then we're going to find the velocity. So we're going to find both of these now. All right, now, first off, delta D, because we're finding speed here, so I'm going to write it over here. We have V is equal to delta D over T. Now, something to look at here is that the wording here, a car drives. So this isn't telling me this car is 250 kilometers west of Waterloo. It tells me it's driving there to Waterloo. These are all displacements, because they're not referring to a position. It's actually referring to a movement. So they're all displacements. All right. But in a case of our car here, when I want delta D, it's all about the distance traveled, the total distance traveled. Well, in which case I don't care about direction. So the first movement I make is 200, or this person does, is 215 kilometers. Then they drive another 115 kilometers, and then finally 80 kilometers. And so that is for a grand total of, let me see here, do the math, 410 total kilometers that they've driven. Again, I do not care about direction because it's speed. All right, again, my T, how much time's gone by for all that driving? 6.5 hours. All right, and so now I can substitute into my formula here. I know my delta D is 410. And the weird part is when I say delta D, that could mean distance or displacement. It all depends on the arrow. The arrow tells you what I'm talking about, just like speed and velocity. They're both V. All right, my time here, I'm going to plug in 6.5 hours. All right, I divide those two to get my velocity, or sorry, my speed. Got to watch my language here. Again, we're getting a decimal answer here to 2 decimal places. I'm getting 63.08. And again, kilometers division means in English means per, so kilometers per hour. So I'll put those units in. Units are important. All right, so there's my speed of the car. Now I get to velocity. Now with velocity here, same formula somewhat, except for I have my arrows. So I have my V equals delta D over T. Again, the difference here is the arrows, the vectors. Now again, my time here, it doesn't matter. It's still going to be 6.5 hours. All right. Now my displacement, that's what I need. That's where I care about direction because displacement is different than distance. And so as I mentioned earlier, my habit is to always, and it doesn't matter as long as you keep your signs straight, I always make west negative, east positive, same idea with north and south. And so my first displacement here that I add up is the car drives 215 kilometers west. So that's a minus 215 because it's west. Then it drives east 115. So I'm going to go plus sign 115. All right. Then back 80 kilometers west. So again, it's traveling west. So I'm going to put a negative sign on that. All right. Now I add those numbers up, or in this case, subtract them. Minus 215 plus 115, a minus 100, it's minus 180. All right. But again, when you are writing down a displacement, it needs magnitude and direction. And so that minus 180 is telling me that's actually 180 kilometers. And again, because it's negative, this is the same thing that happened last time out here. It's actually displacement is west. And so now when I plug in to my formula here, where I have velocity is equal to 180 kilometers west divided by my 6.5 hours. And I divide those two. How am I looking for decimals here? I am getting a decimal again here. Okay. 27.69 kilometers an hour. And again, velocity has direction. And so we're looking at west. So here's an example where our speed and our velocity, the magnitude of them is not the same. And the reason for that, the magnitude is only the same in one situation, and that is when you have uniform motion, where the object goes in the same direction and at the same magnitude for the entire trip. And that is the only time where your speed and velocity will have the same magnitude. Of course, speed doesn't have direction, so they can never be the same. All right, next up. The following graph here represent the motion of a dog. All right, distance north of a house. All right, so this is our delta D here. And what we're going to look at is the average speed of the dog after 10 seconds, given a distance time graph. All right, so here's what we're going to use. We're going to use our formula that we just used, where I'm finding speed here. So V is equal to delta D over T. The only thing is this time is I'm going to use my graph to find the information. And so it says, what is the average speed of the dog after 10 seconds? Well, first of all, that means my time is 10 seconds. All right, but what we need to look at is our delta D. What distance did they travel? All right, so I go over to 10 seconds. I go up, and that distance is 50 meters. It's in meters, yep, 50 meters north, but we don't care about direction. All right, and so if I look at now substituting into my formula where I have 50 is the amount of distance traveled, and in 10 seconds. All right, now I divide those. Well, 50 divided by 10 I know is 5. And again, the units division means per in English, meters per second. And there we go. All right. What is the average velocity of the dog? Well, guess what? I'm going to use the same formula here. All right, so I've got delta D with the arrow, which means displacement, right? And once again, my time here is 10 seconds. But now I got to find the displacement after 10 seconds. All right, so there's two different movements here, or lack of movement. But it looks like in that first 10 seconds, the only thing that this person's done is gone 50 meters north. Start backtracking here, so we'll have to watch out for that. But so our delta D this time is 50 meters. Try to put that in there, north. There we go. All right, so again, I'm going to plug into my formula here. All right, 10 seconds. Forgot my direction there. That's important. And of course, I divide those two. And I get 50 meters per second, or 5 meters per second north. So actually, I was a little bit wrong on that uniform motion thing because they do have the same magnitude here, but they did go in the same direction. So long as they go in the same direction and have the same average speed, then they will have the same magnitude. But again, there's my velocity. Again, going back to speed after 14 seconds. All right, so surprise, surprise, you know what formula I'm using. V equals delta T over T. All right, again, now we're looking at 14 seconds. So now I have to figure out the distance this dog traveled. So again, I go back up to the graph. And at 14 seconds, let's see here. So the dog traveled 50. So I'm gonna do my tally over here for 14 seconds, delta D. All right, so I have traveled 50 meters. All right, then the dog didn't move, right? Because just standing still here for a bit. Maybe it saw a squirrel or something. All right, then look at from 10 to 12, the dog traveled, went 50 meters, or sorry, from 50 to 70. So that dog traveled another 20 meters. And then the dog looks like it ran home, right? Because this is distance from the house, or distance north of the house, because we got to have direction here. The dog ran home, and it ran a total of another 70 meters. And so 50 plus 20 plus 70, that's 140 there. All right, so I go down. The distance is 140 meters because, again, distance is the total travel. Don't care about direction, whether it went back or forth or not. So I got 140 meters as my distance, divided by my time, which is 14 seconds. And I divide those two numbers. I get 10 meters per second. Fast dog. All right, now over again. What was the average velocity? So again, guess what formula I'm using? V equals delta D over T. All right, again, we got our arrows. Time, again, is easy. That is our 14 seconds. I'm just going to plug that in here. There we go. Now the displacement I got to figure out. So again, the displacement is all about going from where you started to where you end in the 14 seconds? Well, let me see here. I'm going to try to erase screen line here. There we go. All right. So let's see. Counted up the first part. The displacement, the dog ran, well, look at the first 12 seconds here. It ran 70 meters north. First, it ran 50. So let's do that. We'll go with delta D here. Figure a displacement. So I total up all the sections here. So in section A, the dog went 50 meters to the north. Oops, bad bracket. North. All right. Then the second part, B, it didn't go anywhere. So 0. Then C, it went another 20 meters north. Let's see here. All right. And then the last stretch, the dog ran back home. So that's plus 70 meters. But it ran back home, so it went in the opposite direction of north. It is south. All right, now, again, when I add these up, for my displacement is that I'm looking at north is positive, south is negative. So that 50 north is a 50. 0 is 0, so I'm not going to worry about it. Then I have another 20 north, so I'm going to add 20. Then I have 70 meters south. South is negative, so minus 70. Well, 50 plus 20 minus 70 is 0. So my displacement is 0. The reason being, again, displacement is marking in terms of magnitude and direction from where you started to where you finished. Well, the dog started at home and ran home. So it didn't end up going nowhere. So 0. And that means the velocity is 0 meters per second. This is the only time the velocity does not have direction, is because it's 0. When you have a length of 0 or a speed of 0, you're not going anywhere. So there is no direction. So that is one example of when velocity has no direction, or I want to say the only one. All right, so that is speed and velocity. So we looked at finding it from a graph. All right, reading off a graph, and then, of course, using our equations, where sometimes the magnitude of our speed and velocity is the same, and most often it is different. All right, so let's see